West Virginia. Doesn't it look like it? No. Okay. Well, anyways, I've got my daughter Ellie here, the creator of the joke book, to deliver joke of the day because it is the best part of the day, and quite frankly, she delivers jokes better than I do. So, Ellie, are we ready for joke of the day?
Yes.
All right, let's have it.
Why did Star Wars episodes 4, 5, and 6 come out before episodes 1, 2, and 3?
I don't know. Why?
Because in charge of scheduling Yoda was. With that, I will take my leave.
And with that, let's get in charge of multiplying rational expressions. Okay, so first, let's recall what a rational expression is. Remember, the word rational means can be written as a fraction. Doesn't mean rational dude. It means can be written as a fraction. So what's going to happen here is we have complicated fractions because they are expressions, and that means there's no equal sign. But we're going to take our complicated fractions that are going to have more than just numbers in the numerator, more than just numbers in the denominator. We're going to multiply those fractions together. So we need to understand that if we're multiplying these rational expressions that are really just fractions, that's really all they are, complicated fractions, yes, but just fractions. That means the multiplying rational expressions is going to be just like multiplying fractions. So we need to recall what it takes to multiply fractions. In other words, what are the steps for multiplying fractions? And if you've ever been a part of my class, you know that whenever we multiply fractions, we go back to elementary school and we say, okay, the first time you ever learned what multiplication was, what was that symbol? Sure, it was an X. So now everybody make an X. Yes, even you watching, make that X. So when you make that X, what happens is you have created diagonals. And so recall that when you multiply fractions, because the X is for multiplication, when you multiply fractions, you cancel on those diagonals. And then after you cancel on those diagonals, you shoot straight across. So remember, that means you're now in my gang. That's right, we're a part of that math gang. So anyways, when you multiply those fractions, you cancel the diagonals and then you shoot straight across. Now recall, I said technically you should also cancel up and down, but I said, oh my gosh, this makes what is a crazy gang symbol even kind of sillier than that. So if you see me and you go, I'm going to be like, oh my gosh. You cancel the diagonals, technically you cancel up and down, and then you shoot straight across, because if you cancel up and down, I promise that when you shoot straight across and you multiply across the numerator, multiply across the denominator, I promise it will be simplified in the end. You don't even have to try to simplify it. So, the steps then for multiplying those fractions are that you cancel on those diagonals, and up and down. Very important that you cancel up and down as well. And then you multiply across. Across that numerator, across that denominator. But the catch is, as I take a look at what I've got down here, these rational expressions, when I try to cancel on those diagonals, I'm going, oh my gosh, there's way too much there. So recall that in order to cancel, you have to cancel factors. And remember, you can only cancel factors. That's all you can cancel. You cannot cancel things that are added. You cannot cancel things that are subtracted. You can only cancel things that are multiplied. Factors are multiplied. So what I'm going to do then, in order to figure out how I'm going to cancel on these diagonals and how I'm going to cancel up and down, I am going to factor those numerators and those denominators. Factor all the numerators and all the denominators. So in my first example, when I multiply these two rational expressions, I'm going to factor that numerator, denominator, numerator, and denominator. I'm going to cancel on those diagonals. I'm going to cancel up and down, and then I'm going to shoot straight across. So when I go to factor this numerator, recall that means I'm going to first always look first to see if there's something common that you can divide out of every single term. And remember, it has to be divided out of every single term. So there is nothing common that I can divide out of each one of these terms. That means I'm going to head for that double parentheses, and I'm going to eliminate half my guesswork right here. This sign, because it's a minus, means that I've got opposite signs. One's a plus, one's a minus. I'm going to break this up into the front slots, X and X. I'm going to break the 15 up into the back slots, which means I want two numbers that are going to multiply for 15. They're going to subtract for a 2 because these signs are different. So the two numbers that will multiply for 15, subtract for 2, are a 5 and a 3. So I'll put my 5 here. I'll put my 3 here. I'm just going to check those outsides and insides to see if I've got it right. Out here I get a negative 3x, and here a positive 5x. That gives me a positive 2x. Remember, right number, wrong sign just means switch signs. Don't switch the numbers, because if you switch the numbers, if you've got something other than a 1 and a 1 there, you're going to totally mess up your numbers. So right number, wrong sign means switch signs. Out here I have a positive 3x, and here a negative 5x. Yep, that gives me the negative 2x that I wanted. So that is factored correctly. Now this denominator, there is no way to factor it. There's nothing common that I can divide out of every single term. So I'm going to leave it alone, and I cannot factor it into a double parentheses. So now I'm going to look at this numerator. And yet again, I'm going to always look first to see if there's something common that I can divide out. Sure enough, I can divide an x out of each one of these. So when I divide the x out of here, I'm left with an x. Divide the x out of here, I'm left with a minus 4. And that is all I can do with that, because I cannot take this x minus 4 and factor it any further. This denominator, there is nothing that I can do with it, because there is nothing common that I can divide out, and I cannot set up a double parentheses. So I have factored as much as I possibly can. Now I'm ready to cancel in those diagonals and cancel up and down. So when I look at this diagonal, what is common to both of those? Yeah, they both have an x minus 5. When I look at this diagonal, what's common to both of those? Sure, they both have an x minus 4, so those cancel out. Now I'm going to check up and down here, nothing cancels, up and down here, nothing cancels. So now I'm ready to shoot straight across. So across that numerator, I have an x plus 3 times an x, which I'm going to simply write as an x times an x plus 3. And then in that denominator, I have 1 times 1, which is a 1. I don't need to show a 1 in the denominator, so here's my answer. Now, depending on who your instructor is, depending on what book you are using, it might let you leave your answer like this. I was always taught back in the old days, this is not simplified because there's a parentheses there. I was always taught that I need to distribute through that parentheses in order to make sure that it is completely simplified. But like I said, it depends on who your instructor is, and it depends on what your textbook is as to whether this is the right answer or this is the right answer. Now, let's take a look at our second question. Got one more example for you. The Arctic is going crazy now. Sounds like the polar bears are coming out. So in this second example, recall that I'm multiplying a couple of fractions, and when I multiply these fractions, what's going to happen is I'm going to cancel on those diagonals, I'm going to cancel up and down, and then I'm going to shoot straight across. So when I go to cancel on those diagonals, what I'm going to do is I'm going to... Sorry about that, guys. Polar bear named Doug showed up. What? Crazy things happen in the Arctic. You just never know what's going to happen here. Okay, so where was I? Oh yeah, looking at this last example of multiplying rational expressions, remember what I'm going to do is I'm going to cancel those diagonals, I'm going to cancel up and down, and then I'm going to shoot straight across. So I need to factor that numerator, denominator, numerator, denominator, because the only thing that will cancel is factors. Remember, always look first to see if there is something common that you can divide out before you do anything else. In this numerator, I can divide a 6 out of each one of those terms. So I'm going to divide a 6 out of each one of those. Divide a 6 out of here, I get an x. Divide a 6 out of here, I get a 2. I'm going to do the same thing on this denominator, and look, both of them are divisible by 3. So I'm going to divide a 3 out of each one of those. Divide a 3 out of here, I'm left with a 4x. Divide a 3 out of here, I'm left with a minus 1. Look at this numerator. Nothing common that I can divide out of each term. So I'm headed for that double parentheses, and in that double parentheses, remember this back sign is going to tell me whether they're the same or opposite. One's a plus, one's a minus. I'm going to split this up into the front two slots. Now there's several ways to split up a 16x squared. I can do a 16 and a 1, an 8 and a 2, or a 4 and a 4. But 9 times out of 10, if you can split it evenly, meaning same term, a 4x and a 4x, if you can split it evenly, 9 times out of 10, that's the way it goes. So I'm going to give that a shot first, and if it doesn't happen, I'll go to one of the others. I'm going to split my 1 into the back slots. I'm going to check my outsides and insides. Out here I get a negative 4x, in here a positive 4x. Those cancel, and I needed that to happen because I don't have a middle term. So that is factored correctly. Now in my denominator, once again, always look first to see if there's something common you can divide out, and there is not. So I'm headed to that double parentheses. Once again, back sign here is going to tell me whether the signs are same or opposites. This being a minus tells me one's a plus, one's a minus. Split this into the front two slots, so I have an x and an x. I want two numbers that are going to multiply for 6. They're going to subtract for a 1 because these signs are opposites. So that's a 3 and a 2. I'm going to check my outsides and insides. Out here I get a negative 2x, and here a positive 3x. That gives me a positive 1x. And yet again, when I have right number, wrong sign, just switch those signs. So out here I have a positive 2x, and here a negative 3x. That gives me the negative x that I wanted. So I've canceled everything I could not canceled. I've factored everything I can possibly cancel. Now it's time to cancel those diagonals. So I'm going to check these diagonals. X plus 2 common to both. I'm going to check these diagonals. 4x minus 1 common to both. But recall, I need to check up and down. Awesome. Look at this. 6 and 3 cancels. Because 3 goes into 3 once, 3 goes into 6 twice. And there's nothing that cancels up and down here. So now that I've canceled on the diagonals, canceled up and down, now I'm ready to shoot straight across. So when I shoot straight across here, all I have left is 2 times 4x plus 1. And all I have down here on the denominator is x minus 3. And like I said before, it depends on who your instructor is, depends on what book you're using as to whether this is okay or if you need to distribute that 2 through. Old school, we had to distribute through. So I would have an 8x plus 2 over an x minus 3, but some instructors and some textbooks will let you stop here. Just be familiar with what your rules are. So that is how you multiply your rational expressions. Remember, just like multiplying fractions, which means you're going to cancel in the diagonals, you're going to cancel up and down, you're going to shoot straight across because you're in my game. But the only thing that cancels is factors. So you have to factor everywhere first. Then you can get into that game. So let's take a look at these multiplication problems. I want to consider one more aspect of it, and that's that restriction on the domain. Recall that the restriction on the domain simply means since these are fractions, we do not want to have zeros in the denominators. And so we need to make sure that whatever we look at in terms of being able to put into that x, we need to make sure that what we put in there does not create a zero in the denominator. So what I have here are two fractions being multiplied together. I've got two denominators. Now we looked at restrictions on the domain when we looked at simplifying our rational expressions, but now I want to look at this idea of being able to multiply them and saying, whoa, wait a minute, I've got two denominators now. So when I look at the restriction on the domain, I need to consider this fraction, its denominator, x minus 4, and I want to ensure that that is not a zero. So in order to ensure that that's not a zero, that means that to solve this equation, I would add 4 to both sides. So my x had better not be a 4. That would cause a 0 in the denominator of this fraction because 4 minus 4 would give me a 0. Any other number is perfectly fine. Now when I consider this fraction, once again denominator being here, that means I don't want that denominator, x minus 5, to be a 0. To solve that equation, I'm going to add 5. And that means I don't want my x to be a 5. Because if I put a 5 right here, 5 minus 5 is 0, that would cause a 0 in that denominator of that fraction. So that tells me that any number I can think of, whether it be positive, negative, fraction, decimal, irrational number, any of them are perfectly fine to put in here and here except for a 4 and a 5. Because either one of those numbers would cause a 0 in a denominator somewhere in those fractions. Now, let's take a look at that second multiplication problem that we had. And we also want to consider the restriction on the domain here. So, let me write that down. Restriction on domain. And once again, the whole idea is, because I have fractions here, I want to guarantee that whatever I put in for those x's do not cause a 0 down here, nor down here. So I want to make sure that that 12x minus 3 is not a 0. So I'm going to solve that equation by adding 3. That'll give me 12x equal to 3, which I don't want to happen. Then I'm going to divide by 12. And so what that tells me is, I'm going to slide this over here, that x had better not be a 1/4 because I get 3 over 12. 3 over 12 simplifies to 1/4. Box that up. Because if I put a 1/4 in here, 12 times 1/4 is going to be a 3. 3 minus 3 will create a 0 in that denominator. So anything will work except for that 1/4. But I also need to consider the denominator of this fraction as well. So that x squared minus x minus 6 had better not be a 0. That creates a quadratic equation. To solve quadratics, I can factor, I could do the quadratic formula, I could complete the square. I'm here to tell you factoring is the easiest way to go if it will factor, and it will because I did that right here. So that means that this factors as an x plus 2 times an x minus 3. That had better not be a 0. That's that zero product principle that says if two things are multiplied together to get a 0, one of the two has got to be the 0. So either that x plus 2 is the 0, which I don't want to happen. If that's the case, the x is going to be a negative 2, but I don't want that to happen. Because if x is a negative 2 right here, that creates a 0 right there. 0 times anything at all is 0. And then in this case, x minus 3, I don't want it to be a 0. So that would indicate x had better not be a 3. Because again, if x is 3, that puts a 0 right here, meaning the whole thing will be 0. That creates a 0 in the denominator of that fraction. So my restriction on my domain is that x had better not be a 1/4, it had better not be a negative 2, and it had better not be a 3. So hopefully that helps with the idea of being able to multiply fractions and looking at the restriction of the domain. Have a great day.